Hello and welcome. Second lecture on Fourier series. So just a quick introduction. You'll be advised to watch the first lecture on the topic where I've done the Fourier series of f of x is equal to x in the interval minus pi to pi. Today we're going to do a slightly more complicated function. F of x is equal to x squared in some other interval. So first of all, let's remind ourselves what the Fourier series theorem says. It says if f of x is piecewise continuous on some interval alpha to beta, then f of x can be approximated by this thing here. Actually, I did say approximate, not approximated, is equal to if we go to infinity, but it will be approximate, of course, if we take a finite number of terms in this particular series. And the series, it has these quantities in there which they need to be defined. So there has this a naught, this an's and this bn's, and also this L. So the L, first of all, is the half period. So if the interval is from alpha to beta, then beta minus alpha divided by 2, or known as the half period, is your L. And the A0 and the A1, A2, A3, and so on can be obtained by this formula here, while the B1, B2, B3, and so on forever can be obtained by this formula here. Note there is a spare and there's an extra term in A, that's that A naught which is at the front, but there isn't such a thing, there's no B naught in this particular expansion. Okay, so let's, that's just a reminder. Please look at the first lecture to familiarize, and then we'll be able to follow this a lot better. So the function we're going to use today is f of x is equal to x squared. We're going to use a different interval, so the interval is going to be, let's say, from -1 to 1. We've done minus pi to pi the last time. Let's go -1 to 1. Let's start with the Fourier expansion of this particular function. So let's work out some of these coefficients. So in order to write the expansion, I need the a naughts, actually the L in this particular case. Let's write it here as well. L is, of course, 1 minus minus 1 divided by 2, or simply you should be able to see that's a gap of 2 divided by 2 is 1. So this will simplify massively a lot of the stuff. These are all ones really, and 1 over 1s and 1 over 1s and so on. So keep that in mind. So we're going to work out the a naught first of all. A naught is, we're going to obtain from this formula, is of course 1 over 1, which I'm not going to write, and is the integral from -1 to 1, f of x, of course, x squared, the cos of, when I'm putting n is equal to 0, so that's in fact 0, the cos of 0 is 1 dx. And of course, that's very easy to integrate. This is even, first of all, so I'm going to put a 2 to take care of it. And it's going to be 2/3 x cubed, and I'm going to do the integration from 0 to 1, and that will give me a 2/3. Okay, so let's record that up here somewhere. Perhaps let's use some different color pen, so we have some of these quantities already written down, just in case I rub it off at some point and then lose information. So that's the a naught. So next thing we need to do is perhaps to work out now the an's, where n now is going to be 1, 2, 3, 4, 5, and so on forever. So now again we're using the same formula. So an is going to be 1 over 1, and we're integrating from -1 to 1. F of x is x squared. The cos, this is 1 here, the cos of n pi x dx. It's a mess. It's a double integration by parts. This is, of course, even. We can actually perhaps write it as the integral of 2 lots of x squared cos n pi x dx, and integrate instead from 0 to 1. Make life a little bit easier, but we still cannot avoid the 2 integrations by parts. So I don't know which way you do your integration by parts. Make sure you follow a method or your method that works well for you. I'll do it in a very specific way, which of course I'm not going to be discussing here. So this is now a 2x squared differentiates to 4x, and a cos of n pi x comes from a differentiation of a sine n pi x, and we need at the front 1 over n pi. Okay, so this is now my little sorter, and when I do that, I'm going to get the product of this column. So I'm going to get a 2x squared over n pi sine of n pi x. That's to be integrated between 0 and 1. and then I'm going to have a minus. I have to write a little bit slanted because I didn't plan it very well. Minus the integral from 0 to 1 of the product of this diagonal. The 4 over n squared, I can write it outside. It's independent of x, of course. 4 over, and the pi as well. Sorry, I didn't even see that. 4 over n pi. And inside the integral, I will have x sine of n pi x dx. Let's start some evaluations here. This actually is not too bad because, of course, it's 0. On the bottom limit is 0 clearly because of the x squared, when you're putting x is equal to 0. And when you're putting 1, the sine of n pi, if n is an integer value, then of course it will be 0. And therefore, at least we have some luck there. So we now need to do the integration of minus 4 over n pi 0 to 1 x sine of n pi x dx. And what shall we do for that? Quite clearly, another integration by parts. I'm going to be rubbing some of this stuff. Maybe not a good idea because I made a mistake. I cannot really check now, but it's too late now. It's already done. Okay, so here we go. X on the top left differentiates to 1, and the sine of n pi x comes from a differentiation of a cos n pi x. Cos differentiates to a minus. He also will produce a 1 over n pi. So this now will produce a minus 4 over n pi bracket. Product of this to be evaluated, so it's going to be minus x over n pi cos of n pi x to be evaluated between 0 and 1 minus the integral of the product of this diagonal. So it's going to be, first of all, a plus. The 1 over n pi I'll write at the front, the cos of n pi x dx between the limits of 0 and 1. And of course I need to close this bracket because everything is multiplied by this quantity at the front. Okay, what happens next? Minus 4 over n pi. When we're putting 0, first of all, it will kill this because of the x. But on 1, it's still going to have a contribution. It's going to be minus 1 over n pi cos of n pi. X is 1. And at the same time, I'm going to do this integration. That comes from differentiating a sine of n pi x. Sine differentiates to a plus. That's all good. And it will produce another n pi at the front. So n squared pi squared. And that's a plus, and that is to be evaluated between 0 and 1, close brackets. Very, very messy sometimes, so it's important that you're very, very neat and organized when you're doing this kind of work. It can be tedious at times. So first of all, this has no contribution because, of course, when you're putting 1, the sine of n pi for all integers is, of course, 0, and sine of 0 when you're putting 0 is 0. So this, in fact, gone. So let's tidy the final bit in there. So it's going to be a positive 4 over n squared pi squared cos of n pi. And as in the first lecture, this is a result that does occur very often. You need to be familiar with it. I'm not going to be singing a song about it. You should know that the cos of n pi is minus 1 to the power of n. It's a standard way of writing a cos n pi in mathematics. Okay, so let's write now this particular coefficients. So that's the ANs now, where n is 1 upwards, is going to be equal to 4 minus 1 to the power of n over n squared pi squared. Okay, we don't need the workings now. And we got, of course, to work out the BNs. I claim the BNs without having done the question. They're going to be 0. All the BN coefficients will just vanish. A lot of the work on Fourier series to do with odd and even functions, as you probably noticed already. And therefore, if you look what's going to happen here, because x squared is an even function, so let's look at the BNs. The BN definition is, of course, here. It's going to be for us here now, 1 over 1, because L is 1, the integral from minus 1 to 1, f of x, which is x squared, which is even sine of n pi x. L, of course, is 1. But, of course, this will be 0. This is even. This is odd. Multiply them together will produce odd. Odd in a symmetrical domain is, in fact, 0. And, therefore, let's record that the bn's, we haven't forgotten them. In fact, the bn's turn out to be 0 for this particular example, okay? So our expansion will only have causes. It's a cos expansion. So how we just found now? Okay, let's write our expansion. So we found that f of x, which of course is our x squared, in this particular interval can be approximated by this quantity here. So the a naught was 2/3, divided by 2 is simply 1/3, plus the sum from n is equal to 1 to infinity. There's no bn, so there's no sign bits in there. It's just this quantity here that we've worked it out to be this coefficient, 4 minus 1 to the power of n over n squared pi squared. And of course, in our case, the L is 1, is going to be the cos of n pi x. Okay, and this is in the inside this the sigma notation. So if you think about what is going to be our expansion, the same way we have polynomial expansions in Maclaurin and Taylor, now we'll have an expansion causes. Okay, so it'll be the cos of pi x, the cos of 2 pi x, the cos of 3 pi x, and of course these coefficients at the front will be adjusting, but be an infinite series, but in causes. Okay, and this is now what this series is all about. Fourier series about sines and cosines. So let me just do one more thing for this particular question, since I just saw it in there. We can actually use this particular, it's not the standard way, there's another way we can do this one with f of x is equal to x and Parseval's identity, but we can actually prove a very important result. I'm going to write it here. So that's a little bit of an aside. The sigma from n is equal to 1 to infinity of 1 over n squared, a very famous result, is in fact pi squared over 6. We can actually use this particular result to actually find it, and I'll show you how. So let's see how we can actually get this from this expansion that we just produced. So that's an extra bit. Perhaps I should do another lecture, but the problem is I have to derive this result before I can actually do it. So I'll do it here. So if you look at this expansion, okay, I can substitute into this expansion a number, and the number that suits me is in fact 0. Sub x is equal to 0. So what will happen? X squared, which in fact is 0, will be equal to 1/3 plus sigma from n is equal to 1 to infinity. And what am I putting? X is equal to 0. So that's the cos of 0, which is 1. So basically, this will be a 1. So it'll be this infinite series. And let's see what we can do with this one. All right. So we can definitely say, as the next line, if I subtract this term to the left, I'm going to get minus sigma from n is equal to 1 to infinity, 4 minus 1 to the power of n over, perhaps I should have more tidies there. I'm just not thinking ahead. I'm very tired today. All right. I'm going to do it here, though. I'm going to look what is independent of n. Okay, so this pi squared and this 4, I can actually put it outside. So we can actually write the 4 on the outside, the pi squared on the outside, and let's forget the minus that we had there from the beginning, and let's rub them off from inside the summand. So the pi squared has gone. So let's see what we have obtained so far. Is equal to 1/3. So quite clearly, what we got in there is the sum from n is equal to 1 of minus 1 to the power of n over n squared is going to be minus pi squared over 12. Okay, what does that actually mean? What numbers that do we get from this? We're getting, of course, minus 1 plus 1/4 minus a 9th plus a 16th minus 1 over 25 plus dot dot dot. This is definitely minus pi squared over 12. No problem. That's fine. They're quite evidently 1 minus a quarter. I'm doing like that so it's easy for us to see here. Yeah, I normally would have done it, but I won't be showing this kind of working. Basically, if we add there now an n plus 1, I can lose this particular plus. Sorry, minus to a plus. So that is minus 1/16 plus 1 over 25 minus dot dot dot. It'll definitely be pi squared over 12. And let's see what we can do now. So in order to adjust it, so I've just said, okay, if I put another, multiply by another minus 1, it will make that into a plus. So that is basically this line here. And somehow I need to go from this line to this line. Okay, let me just show you how I'm going to do this. This I'm going to rub it off. We don't actually need it. Okay, if I add, so I use a different color pen. Pink is a good pen. I hope it doesn't write too fat. 2 over 4 plus 2 over 16. And then, of course, I'll be adding, let me just write one more term in there so you can actually see. There's going to be a minus 1 over 36 here, dot, 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 and add another 2 over 36. I don't know what that is equal to, but certainly if you see what is going to happen in there, that plus that is going to give me 1. 2 quarters, take away a quarter is of course a quarter, plus a 9th, plus 1/16, plus 1 over 25, plus 1 over 36. And of course, I wish I could write pi squared over 6, but I don't know what it is. At this moment, I'm going to say it's equal to s because I'm trying to prove that it's in fact pi squared over 6. So I'm going to say the following. If you look now at these two lines, I say definitely pi squared over 12, this bit here, plus 2 over 4 plus 2 over 16 plus 2 over 36 plus dot 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 forever is of course what I'm after. The question is, what is this now? Let's have a look. I'm going to write in sigma notation because of course it is actually easier. This 2, I'm going to write that on the other side. I'm going to factorize the 2 on the numerators. And this is going to be from n is equal to 1 to infinity, 1 over 2n all squared is equal to my s. I need to make some room somewhere else because I'm desperately running out of space. Do I need any of this? The answer is probably not. So let's clear some of this space and let's take it a step further. So I'm just going to merely rewriting this. Pi squared over 12 plus 2. This I can expand it. So I can actually say, okay, no problem. That is going to be 1 over 4n squared is equal to my s, where my s, of course, is the desired sum, the very famous sum that I'm trying to find. But I've noticed I've got a quarter, which I can factorize outside the sigma. And not only that, that's not the interesting thing. The interesting thing is what this sum has now become is, of course, the 1 over n squared from n is equal to 1, 2, 3, which is, of course, what I'm after. And therefore, this quantity here is definitely another s. So pi squared over 12 plus 2 over 4, which is a half. This quantity here, I called it s. This is just this quantity here, which is, of course, the same as that, plus a half s is equal to s, probably double both sides of this equation, pi squared over 6 plus s is equal to 2s, and the result follows. S, subtract the s to the other side, is of course pi squared over 6. Isn't that beautiful? Okay, and very, very efficient. So this is a way we can actually get this particular result through Fourier series. Not the only one. We can actually use a different function, Parseval's identity. That's the one that I was taught. I remember as a student, but you can do it in many different as other series. Okay, I hope you find this useful. I hope you followed it, and I'll be signing out. I'll see you very soon.